Okay, let's do another or a few more examples. This time we are focusing on this last technique, which is to multiply the numerator and the denominator by the same factor. Okay, so the first example that we want to do is example number 7, and it is the integral of 1 divided by 1 plus sine x. Now this technique is actually going to be, this is going to be on the tricky side, because the question is, how do you know what you should multiply the numerator and the denominator by? It's very similar to rationalizing a denominator, where you know, maybe if you have a square root in the denominator, and so you kind of multiply by a factor which is going to capitalize on the difference of squares. So we're going to do the same thing here. We're going to multiply our integrand, right, which is 1 plus sine x, on the top and the bottom by 1 minus sine x. And when we do that, in the denominator, we're going to get, what do we get? We'll get 1 minus sine squared x. Perfect chance for us to remember that sine squared x plus cosine squared x equals 1. So 1 minus sine squared x is the same thing as cosine squared x. Okay? So we can actually rewrite our integral here as 1 minus sine x divided by cosine squared x. Okay? So now our integral of 1 divided by 1 plus sine x dx is equal to the integral Let me actually clean this up a bit. Okay. Is equal to the integral of 1 minus sine x divided by cosine squared x dx. We're going to separate this integrand, so we'll have 1 over cosine squared x minus sine x over cosine squared x. Now we'll have the integral 1 over cosine squared x dx minus the integral of sine x over cosine squared x dx. Our first integral here is the integral of secant squared x dx. From our formula, from our table, we need to know that the integral of secant squared, that's just equal to tangent of x. How do you know that? Because the derivative of tangent of x is secant squared x. So this is one of those facts from the table that we have. Let's look at the second one here. For the second one, we've got the integral of sine x over cosine squared x. This is a perfect opportunity to do a U-substitution. So if we let u equal cosine x, then du is equal to negative sine x dx. Okay, so that means that we can rewrite this as plus, come on, she, get out of here. We can rewrite this as 1 over u squared du. And the integral of 1 over u squared du, that's the same thing as the integral of u to the negative 2 du. Remember, we add 1, which is going to get us u to the negative 1, and divide by negative 1 and plus a constant. But we're not done yet, because our answer needs to be in terms of x. So we actually need cosine. So we've got cosine x to the negative 1 divided by negative 1 plus a constant. Okay, that's the same thing as just negative cosine x to the negative 1 plus a constant. But what is cosine x to the negative 1? That's 1 over cosine x. And that is the same thing as secant x. Okay? So all of this, and we've got our tan x that follows. Our tangent follows each of these little computations. I'm not going to write this each and every line, but our final answer is going to be tangent x minus secant x plus c. All right. Let me just actually verify that I didn't make a mistake with my negatives and positives. So, easier than going back and tracking each of these equations is for me to say, what is the derivative of tangent? Okay, and the derivative of tangent is going to be...
It's 2045.
Is going to be secant squared x. I've got that memorized. And what's the derivative of secant? The derivative of secant is secant tan. So, this would be secant squared x minus secant x tan x. Is that what we started off with? Well, this is certainly secant squared x. And if I rewrite this as 1 over cosine x times sine x over cosine x, then I've got tan x and secant x. Right? So in fact, if I had written originally sine x over cosine squared is equal to secant x tan x, then I could have just said the integral of secant x tan x dx is equal to secant x. This is plus c. This is on that table. So this is actually kind of the perfect example of how knowing that table will save you time, right? Because that's what, 1, 2, 3 steps, as opposed to all of this that I had to do when I used U-Substitution. Okay? So I was able to verify and check, and I can say that this is my final answer. Okay. So now let's do this other example here. Again, we still have the same strategy. This is another example of this strategy being used, where you multiply the numerator and the denominator by the same factor. The question is, what is my numerator and my denominator? Right? What should I multiply the top and the bottom by? And it turns out that the following works. So we're going to multiply. First, let's actually rewrite our integral so that it's easy to see. So we've got dx. Let me choose a different color. So the integral of dx divided by 1 plus e to the x. We can actually write that as 1 over 1 plus e to the x dx. Okay, now that we have it like that, what are we going to... We now see it's easier to see the fraction that we have. We're going to multiply the numerator and the denominator by e to the negative x. So we have 1 over 1 plus e to the x, e to the negative x in the numerator, e to the negative x in the denominator. Okay, so now we've got the integral, e to the negative x in the numerator, and in the denominator, I'm going to need to distribute because I've got 1 plus e to the x times e to the negative x. Okay. And when I distribute, in the numerator, I'll still have e to the negative x. And in the denominator, that's going to give me e to the negative x. But now this e to the negative x times e to the x is going to give me just a 1, right? Plus 1. And now I can say, oh, I forgot my dx. Now I'm ready for a U-Substitution. Okay, so my U-Substitution is going to be, let u equal e to the negative x plus 1. Then du is going to be negative e to the negative x dx. This part right here is just perfect because it shows up as part of my original integral. Okay? So I'm going to be able to rewrite this integral. Let me put in my little arrows. I like the arrows because it tells everyone that what we're working with is a recipe. Right? So I know that this is how I'm getting this equal sign. So I'm going to have this e to the negative x dx is the same thing. Do you see how e to the negative x dx is equal to negative du? I multiplied both sides by negative 1, so that negative is going to cancel, and this du is going to turn to negative du. So I'm going to have negative integral du. And then what about this 1 over e to the negative x plus 1? That's just 1 over u. Okay? And I already know that this is going to be equal to negative natural log of u plus a constant. But what is u? U is e to the negative x plus 1. So I get negative e natural log e to the negative x plus 1 plus a constant. And all of that is written very, 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 very small. So I'm going to just go ahead and write it larger. This is our essential solution. 1 plus e to the x ends up being negative natural log e to the negative x plus 1 plus a constant. Okay? And then I kind of want to show you another method. So it's the same integral, right? It's the same integral, but I want to show you another method. Instead of multiplying the numerator and the denominator by the same factor, we're going to do that trick that we did before, where we're going to add and subtract the same factor so that we're essentially kind of rationalizing this polynomial in e to the x. So let's see here. So we've got the integral dx divided by 1 plus e to the x. First thing I'm going to do is rewrite it so I can actually see my fraction. Okay, so my dx is off to the side. Now what can I add and subtract to make this look a little different? Add and subtract e to the x. See, if I have 1 plus e to the x, right? But I can't just stick in an e to the x. I have to subtract off the same amount. So now what will I have? I will have 1 minus e to the x divided by 1 plus e to the x dx. Now this is wonderful because the integral of 1, that's easy. It should be easy, right? What's the integral of 1? Integral of 1 is just going to be x. And then for this backhand, for this last part here, I'm ready for a U-substitution. I'm going to do U-substitution. Let u equal 1 plus e to the x. du is going to be equal to e to the x dx. So I can rewrite this as 1 over u times du, and I'm trying to integrate that, which is going to give me the natural log of u. But remember, u is 1 plus e to the x, so I've actually got natural log of 1 plus e to the x. Okay? And then, yeah, we can kind of indicate that how we got the equality sign is with the substitution. So, for my answer, I'm going to have x minus the natural log 1 plus e to the x plus a constant. Okay. Now, at this point, you should be asking yourself, excuse me, hey, wait a minute, Kalila, are you trying to pull a trick on us? Because that does not at all look like this, right? So if we integrated the same integral, one time we did it, this is what we got. Y'all see that? The second time we integrated, we got that. This one has an x in it, right? So this is my look. It has an x in it. How can this possibly be the same as this? Right? I'm going to leave that for you to figure out. Have I made a mistake? So that's the practice question. Why, or not even why, because that's presumptuous, is natural log e to the negative x plus 1 plus a constant the same as x minus natural log, oh man, this looks different, x minus natural log e to the x plus 1 plus a constant, right? Because you can say, oh, this looks weird, Cleela, because we've got the negative x. Do y'all see that? And this is just a regular x. This one has an x, and this one has no x. You know, right? What's going on? That's the question. The question is, what's up? What is up? And then the answer, you tell me. All right. Thank you.